Hello and welcome to the final presentation for Team 12 for ME 452 IST 528. Our team has decided to perform an analysis and redesign of a mechanical pencil sharpener. Our team members are Joy On, Connor Barash, Ariana Bressler, Alexandra Leone, and Patrick Okimi. The mechanical pencil sharpener is a tool that sharpens the writing point of wooden pencils, which is powered by a hand crank that rotates a cylindrical cutting apparatus in the sharpener. For the sharpener, our primary customers are students and teachers, while secondary customers are artists and office workers. Here's an exploded view of the original design. This view allows our team to better understand how the sharpener functions.
The function analysis system technique, or FAST diagram, highlights the functions of a mechanical sharpener. Specifically, the task function is to sharpen a pencil, and the primary basic functions are to remove material and stabilize the pencil. Supporting functions are based on improving convenience and ease of use. The function component mapping matrix shows that all the components in our mechanical pencil sharpener has functions. Some key functions include guiding insertion and preventing breakage. Some key components that serve multiple functions include the case, sharpening blade, and pencil grip.
Primary customers for this product will be teachers and students who will use the pencil sharpener frequently for sharpening basic sheet pencils and colored pencils, while the secondary customers will be artists and office workers who will use the sharpener personally for more specialty and high-quality pencils and colored pencils.
For our product family design, we have created a functional differentiation table. Here we are showing which functions are the same for our primary customer group, which are students and teachers, and our secondary customer group consisting of artists and office workers. Also shown are the functions that are different for each customer group, which are allow portability, contain savings, and provide adjustability.
From our functional differentiation table, we were able to figure out which modules we will have for our product family design. Modules will include the shavings tray and the crank handle.
The first part we decided to modify for our secondary customer group was a shavings tray. Because portability and ease of use is more important than the amount of shavings it holds and the price, we decided to slant the bottom of the tray in order to have less hard crevices to clean, and also have a cap that you can remove in order to dump the shavings without taking the tray out.
The second part we changed for the secondary customer group was the handle. At a slight increase to price, we increased the handle length in order to accommodate for the larger hands of the secondary customer group. This increases comfortability and ease of use for the secondary customer group. Here you can see the CAD models for the primary and secondary customer groups.
In the design, there were two parts that could change, the crank handle and the shavings tray. In the original assembly sequence, the crank handle was assembled early on. This caused assembling to be inefficient as the parts with the two divergent paths, as shown in the upper picture, had many common parts after the divergence. Therefore, a new assembling sequence was constructed, as shown in the lower picture, where the different part options weren't assembled until the last few steps. This helped delay any divergence until completely necessary, which increased efficiency and decreased assembly cost.
In our initial analysis for design for manual assembly, our total assembly time was 80.53 seconds, and the assembly efficiency was 48.4%. We chose to redesign the back plate and crank handle, highlighted in yellow, due to their high assembly times and associated costs. After the redesign, we performed a final analysis of design for manual assembly and found the total assembly time was reduced to 53.93 seconds, and the assembly efficiency improved to 72.3%. Here we show the before and after of our platform part redesign, the back plate. This redesign uses a snap fit in order to eliminate fasteners, creates a toolless assembly, and makes the part much easier for manual insertion, reducing the overall assembly time by 23.6 seconds. This redesign followed Design for Assembly Guidelines 1, 3, and 10. Here we show the before and after of our modular part redesign, the crank handle. This redesign uses a snap fit rather than threads, engravings on the extrusion face to facilitate orientation, and improved locating features with the addition of the extruded interface. These improvements reduced the overall assembly time by 3 seconds for this part. This redesign followed Design for Assembly Guidelines 3, 7, and 11.
Next, we redesigned the cover subassembly, which includes the inside cover, backplate, outside cover, pencil grip, and pencil grip wheel. We chose this subassembly to redesign for automated assembly because it was previously expensive but has crucial functionality. In our initial analysis, the backplate and pencil grip wheel were most expensive, with a total assembly cost of $4.60. Once the backplate and pencil grip wheel were redesigned, the total assembly cost decreased by 19%, with a total assembly cost of $3.73. First, we redesigned the pencil grip wheel. We added ridges to provide a locating feature where the pencil grips sit on the wheel, following design principle DFA 11. Next, we added extrusions at the slots to allow for ease of insertion of the outside cover into the wheel's slots, following the design principle DFA 10. Lastly, we chose to make the extrusions ovals that are symmetrical in 2 axes to increase part symmetry, following design principle DFA 6. Next, we redesigned the backplate. Similar to the pencil grip wheel, we added extrusions for easy insertion where the outside cover is inserted into the backplate, following design principle DFA 10. We made the diameters of these extrusions larger than the diameters of the rods to prevent tangling, following design principle DFA 8. Lastly, we added a triangle on the lower right of the backplate to facilitate orientation, following design principle DFA 7. Now we'll be discussing process selection of these parts.
Here is the process selection for the pencil grip wheel for design for automated assembly. The critical product function is to provide adjustability with the key dimensions of 4.4 and 2 millimeters, which is the location where the pencil grips slide on and is highlighted in the picture below. Based on the part specifications and features shown in the process selection chart, conventional machining is recommended over sheet forming due to its better economic batch size. Here is the process selection for the backplate for the design for automated assembly. The critical product function is to maintain stability with the key dimension of 4.4 millimeters, which is the diameter of the rail to extend support of the pencil sharpening and is highlighted in the picture below. Based on the part specifications and features shown in the process selection chart, die casting is recommended over conventional machining due to its better economic batch size.
Here you can see the before and after the design for manufacturing for the pencil grip wheel. From using the analytical method to calculate the cost, the part cost stayed basically the same at $1.05. Using the Hubs program produced a before cost of 4 cents and an after cost of 10 cents. This discrepancy can be from the estimation used to extrapolate the data. Hubs only sells in bulk up to 1,000 parts, so the data was extrapolated to have a quantity of 1,500,000, which can cause the discrepancies that were shown among the costs.
Here you can see the before and after of the design for manufacturing of the backplate. Using the analytical method, both the before and after cost of the backplate is 46.8 cents. The first change made to the backplate was decreasing the thickness of the bottom corner of the backplate in order to keep a constant wall thickness, which decreases the price of the backplate. The second and third changes to the backplate were adding fillets on sharp corners, one to the screw hole and one to the rod, in order to increase stability for a small increase in price.
In order to assist customers in having the best service possible, the mechanical sharpener can have a blade replacement subscription. This would help ensure that the model lasts longer by giving customers optional different blades that they can swap out and be able to sharpen different materials, improving product efficiency in sharpening the materials and improving customer satisfaction. Furthermore, this would help reduce waste as it would provide the option for returning old blades to be recycled and would allow the product to last longer, cutting back on waste from the outer plastic parts.
The overall redesign of the manufacturing and assembly of the mechanical pencil sharpener allowed for an overall product price reduction of 98 cents. Overall, our redesign provided increased adjustability at a low cost. However, our redesign had some added material, which was the cost of increased adjustability.
Thank you for listening to our presentation. We will now take any questions you might have.